All right, quick recap video. What did we do in section 5.5? The chapter is basically about linearization. What can we do by approximating a function as a line over a short distance? So first thing we said is, well, how do we do that? And of course, there's the equation of the line using point slope form. We use capital L for linearization. And we said that a function is approximately equal to that linearization as long as you are looking at a value of x that is near the value that you chose as the center of your linearization. X equals a is the center of the linearization. What do we mean by near? Depends. It really is going to depend on the function, and it's going to depend on your needs. And so we did calculate, you'll remember that we calculated errors for our linearization. And typically what you'll do is you do a linearization, you calculate an error. If the error is small within what you're interested in, then you just say, okay, linearization's good up to there. There are more complicated strategies where you could set the error, and then that allows you to figure out how far out you can go and still be within that error beyond the scope of this class. So what did we use linearization for? We looked at a few examples. Binomial powers. We said that a power of a binomial, 1 plus something raised to some power, can be approximated as 1 plus the power times the something. And the something could be any function of x. It didn't just have to be 1 plus x. We also approximated roots, and in order to approximate roots, we said, well, let's pick a known root that's near the one that we're interested in. An example was the square root of 123, and we said, hey, look, we know the square root of 121 is 11. Let's center our linearization right there at x equals 121. What else did we do? Differentials. Again, differentials is a linearization. If we say that dy dx is equal to f prime of x, we said that we could linearize this as y equals the slope times x. In other words, we're just making a little linear function right there and saying, well, I know that if I choose some small value of x, I can then predict what my small change in y will be. And that'll come in more useful, again, this whole idea of differentials when we get to integrals. And finally, Newton's method to approximate roots. And again, Newton's method said if you're looking for a root that's right here, you pick some nearby value, you linearize, and you find the root of the linearization, which allows you to then linearize at that root and find the root of that linearization. And every time you do it, under most circumstances, assuming you started close by and you don't have some of the failure points that we talked about earlier, after a certain number of iterations, you will eventually get to, here is the root accurate to as many decimal places as I am interested in. All right, I'm going to wrap that up here. I may come back and try to do one more video illustrating. In fact, I think I will. You'll see it pop up in my channel in this playlist. I'm going to do a video illustrating how that calculator process works in case you're a visual person and the explanation in the part 2 video of Newton's method didn't make sense. So come back and take a look at that if you're interested. Otherwise, thanks for looking.